Look up at the night sky. Even with the naked eye, you see thousands of stars, right? Now imagine a telescope like a Hipparcos. It could potentially observe a million. So here's the question that immediately gets me. From that huge number, how do you even start deciding which stars are the most important ones to look at?
That really is the heart of it.
Yeah.
And it's the core challenge we're diving into today.
Mm-hmm.
You shared some fantastic sources detailing the story behind something really fundamental, the Hipparcos Input Catalogue.
Right.
We're going to unpack the incredible effort and the scientific thinking that went into creating that essential first step for the Hipparcos mission.
Exactly, because, we're so used to missions like Gaia now, which basically hoovers up everything above a certain brightness, an all-sky survey.
Mhm.
But Hipparcos was different. It came before Gaia, designed for super precise measurements, positions, movements of stars, but, and this is the key bit, it needed a specific pre-planned observing program, a list.
A very carefully chosen list. And that requirement, as we'll see, threw up some really fascinating challenges.
Okay, so that's our mission for this deep dive then, to figure out how this list, the Hipparcos Input Catalog, about 100,000 stars, right, how it actually came together.
Precisely. We'll look into the scientific debates, the tech limits back then.
The 80s tech.
The 80s tech, exactly. And contrast that targeted approach with Gaia's observe everything method. It really shows how those tough early experiences drive the amazing progress we see today in astronomy.
Okay, let's dig into that main constraint then. This technology limitation. We're talking early 80s here, no modern CCDs. Hipparcos used something called an image dissector tube.
That's right. And the key thing to grasp is that it could really only measure one tiny point of light, one star, at any given moment. It had this small 30-arc-second sensitive spot,
So literally observing star by star by star.
one by one, which meant the satellite's total observing time was this incredibly precious resource that had to be carefully divided up among the chosen targets.
Ah, okay, so that inherently limited the number of stars it could study.
Absolutely. Limited to around 100,000 over its whole mission. Just a tiny fraction of the million potentially visible stars. You could feel the pressure, right? Every single observation had to count.
And okay, here's where it gets wild for me. Not only did they have to pick this small fraction, but the tech itself meant they needed to know a surprising amount about the star before they even pointed the telescope.
Exactly. To get the detector pointed correctly, they needed the star's approximate position beforehand. And pretty accurately, too, better than 1 arc-second.
Wow.
Plus, they needed a decent idea of its brightness, its magnitude, preferably within about 1 magnitude.
You couldn't just like scan a patch of sky and see what was there.
Nope. No serendipitous scanning here. This demanded a detailed catalog of target stars, fully prepared before the satellite launched. And this catalog wasn't just, a shopping list.
Right.
It was fundamentally deciding which stars future astronomers would have precise distances and proper motions for. A foundational data set.
Okay, so the big question though. How do you decide which 100,000 out of a potential million get the golden ticket? What criteria make a star important?
That was the million-dollar question, wasn't it? Or, well, the multi-million euro question.
Hmm.
And it sparked some really intense discussions. They had to juggle a whole range of scientific priorities.
Like what? Give me some examples.
Well, okay, should they focus on the few known white dwarfs? They're super valuable for understanding how stars end their lives.
Okay, stellar evolution.
Yeah.
Makes sense.
Or prioritize the stars nearest to us. Knowing our local neighborhood is pretty fundamental, right?
Definitely.
But then you also needed stars that represented the different bits of our galaxy. The disk, the halo.
Should get the bigger picture structure.
Exactly. And stars moving really fast across the sky, high proper motion stars, they can tell you interesting things about galactic dynamics, maybe stars just passing through.
Huh. Okay.
And then there's the stars themselves. Binary stars are crucial for figuring out stellar masses.
Right. Watching them orbit each other.
Variable stars, the ones that change brightness, tell us about what's going on inside them. Stars with weird chemical compositions give clues about their history. The oldest stars, the subdwarfs, tell us about the early universe.
It sounds like trying to please everyone with a very limited budget.
That's a great analogy. It was a massive balancing act across so many competing scientific goals. And on top of all that,
There's more.
oh yeah, they needed a good, even spread of these stars across the whole sky.
Ah, for the coordinate system, the reference frame.
Precisely. For building that fundamental celestial reference frame. Think of it as the ultimate map grid for the cosmos. Without reliable anchor points spread everywhere, the map gets distorted.
So some stars might have been scientifically fascinating, but in the wrong place, or in a clump of other interesting stars.
Exactly. Hard choices had to be made. For every star that got in, many others, potentially just as interesting to someone, had to be left out. You can imagine the differing viewpoints.
Oh, I bet. And the sources described this selection process back in the late 70s, early 80s as, quote, competitive, protracted, and torturous affair. Doesn't sound smooth.
Not at all. And, it's interesting. The mission wasn't universally cheered on from the start. Outside the astronomers specializing in measuring positions, the astrometry folks, some scientists saw Hipparcos as maybe a bit of a gamble, a one opportunity thing that might take resources from other fields.
They weren't expecting follow-ups like Gaia back then.
Not with the same certainty or the rapid tech leaps we see now. It felt like a single shot.
And right in the middle of orchestrating this complex effort was Catherine Turon from the Paris Observatory. She sounds like a key figure.
Absolutely central. The descriptions paint her as incredibly passionate, possessing this almost encyclopedic knowledge of stars and just phenomenal organizational skills. She led this team of about 50 astronomers across Europe for more than 5 years.
5 years just to build the input list?
Just the input list, yeah. And her colleagues clearly respected her drive. There's that great little anecdote.
The main...
Yeah. Mais non, that was not what we agreed. Apparently, he said very firmly, but with good nature. You can just picture her keeping that huge, complex project on the rails.
Incredible. So you've got the scientific debates, the tech limits, the personalities. What about the just plain practical problems of dealing with astronomical data back then? It sounds like a different world.
Oh, it really was.
Hmm.
Think about something simple. Star names. The same star might pop up in different catalogs with totally different labels.
Like an alias.
Kind of. Procyon, for instance, a bright, well-known star. It was HD 61421 in one catalog, GC 10277 in another, FK5 291 in yet another.
Whoa! How did they even know they were talking about the same star?
That was a huge part of the work, building the cross-referencing systems we take for granted now.
Yeah.
A lot of that groundwork was done for Hipparcos, just to sort out which star was which.
Okay, that's one hurdle. What else? You mentioned needing positions.
Right. And the surprising thing is, for loads of stars back then, accurate positions just hadn't been measured.
Right.
Or if they had, the values could differ between catalogs.
Why would they differ?
Different reference frames used, different time standards when the observations were made, plus the star's own motion across the sky, its proper motion. Getting everything consistent and accurate to that crucial 1 arcsecond level needed for Hipparcos pointing. That took an immense, painstaking effort.
So, faced with all this, they decided to ask for help, to reach out to astronomers worldwide.
They did. It was framed as this once-in-a-lifetime opportunity, which really underscores how significant Hipparcos was seen even then.
And I remember you mentioned there's a debate about who should get to propose stars.
Yeah, within the European Space Agency committees. Should it just be European scientists, since it's primarily European funding, or open it up?
And they open it up side one?
Thankfully, yes. The altruistic camp, as the source calls them, prevailed. They recognized the science would be better if they pooled global expertise. So, in early 1982, the call went out worldwide.
And the response, was it enthusiastic?
Enthusiastic is an understatement. It was overwhelming. Lists of stars flooded in from astronomers all over the globe. Everyone jumped at the chance. Proposals covered everything. Stars to study galactic structure, nearby stars, rare types like Cepheids and RR Lyrae, stars needed for that fundamental reference frame, important binary systems, even some bright stars in the Magellanic Clouds, and a few asteroids, just a huge range of scientific goals.
Okay, now paint the picture for me. How did this data physically arrive? No FTP servers, no cloud storage?
Get this. Half the proposals came on these big, bulky 9-track magnetic tapes. Reels of tape.
Like in old computer movies.
Exactly. Holding maybe 100 megabytes, which was massive then, and the other half.
Uh-oh. Don't tell me.
Punch cards. Stacks and stacks of cardboard cards with little rectangular holes punched in them. 80 characters per card.
No way. Punched cards in the 80s.
Oh, yeah. It had been the standard for decades. Can you imagine? This Aladdin's cave, they called it, of tapes and card boxes piling up at ESA Center in Noordwijk in the Netherlands before being shipped off to Paris.
That's incredible, just the physical logistics. It's such a shame there isn't a photo of that mountain of data.
Isn't it just? So, okay, you've got this mountain of tapes and cards. Different formats, different lists, overlaps, probably errors. What next?
Yeah, how do you turn that into a single, usable catalog for a space mission?
Monumental task. They had to merge everything, weed out the duplicates, remember the naming problem,
Yeah.
check the submitted positions and proper motions, find regions of the sky that were undersubscribed, and fill those gaps for the reference frame.
And deal with areas where too many stars were proposed.
Exactly. Reconciling those oversubscribed regions, and maybe the trickiest part of all, balancing all those competing scientific priorities we talked about earlier, making the final cuts.
Okay, that sounds like you need some serious wisdom and diplomacy.
Which is where Adrian Blau comes in, a really highly respected figure in astronomy.
Right, you mentioned him, former head of ESO, president of the IAU.
That's the one. He was suggested by Hank Althoff at ESA, apparently. Blau agreed to chair an independent committee specifically to scrutinize all the scientific proposals and assign priorities. Their goal was to ensure the final input catalog was the absolute best, most scientifically valuable list possible.
So, not just the catalog team making the calls, but an independent review.
Yes, a layer of expert oversight. Blau assembled this team of 15 really prominent astronomers from all across Europe.
A kind of wise counsel.
You could call it that. For about 3 years, they met regularly, debated the state-of-the-art knowledge in different fields, nearby stars, variable stars, galactic structure, the reference frame, and worked closely with Catherine Turon's team to fine-tune the observing program.
And these weren't just meetings in sterile conference rooms, right? The source mentions historic observatories.
Yeah, they held progress meetings in places like the Paris Observatory, Nice, Rome, Torino, Heidelberg, Edinburgh, which must have helped. Not just reviewing progress and priorities, but building relationships, trust, and a real collaborative spirit among this international group.
And then there was that one really special meeting, Oswa, in the mountains.
Yes, Oswa, 1985. A week-long meeting for the whole consortium, about 50 people, up in this village in the French Alps.
That sounds amazing.
Doesn't it? Apparently, one astronomer, Bernard Nicolet, used to wake everyone up with an alpine horn.
Seriously.
That's the story. They mixed intense science talks with walks in the snow, evening concerts. Imagine discussing galactic structure surrounded by alpine peaks. Must have been incredibly inspiring.
What a setting. And something else happened there too, didn't it? Related to the person who first proposed the satellite.
That's right. It coincided with the 79th birthday of Pierre Lacroute, the French astronomer, who originally conceived the idea for a space astrometry mission way back.
So they had a party.
They did. A big cake, maybe even some dancing. It's those little human touches within these huge scientific projects that really bring the story alive, I think.
Absolutely. And Oswa was also a chance to connect with some giants of ground-based astronomy, people whose work Hipparcos would build on or even surpass.
Exactly. Folks like Wilhelm Gleis, his catalog of nearby stars is still famous today, and Walter Frick, who was the mastermind behind the FK5 catalog.
What was the FK5?
It was the state-of-the-art star catalog and reference frame before Hipparcos, the gold standard, based on decades of ground-based observations.
So kind of the system Hipparcos was aiming to improve upon.
Precisely. And it's fascinating. Frick, though deeply rooted in ground-based work, apparently became a real enthusiast for space astrometry and gave valuable advice. It shows that transition happening.
It's amazing to think that even before Hipparcos launched, people like Adrian Blau realized how valuable all this preparatory work was, calling it astronomy's great vacuum cleaner.
Yeah, wasn't that perceptive? Cleaning up star names, getting better positions, finding binary companions. The catalog preparation itself was already advancing astronomy.
So after all that 5 years of intense work, debates, punched cards, mountain meetings, it was finally done.
Finally done. April 11th, 1988, there was a formal ceremony at Nordwick. Catherine Turon symbolically handed over the completed Hipparcos Input Catalogue on a magnetic tape, of course, to ESA's Director General at the time, Reimar Lust.
Must have been a huge moment of relief and achievement.
Immense, I imagine. And they even got to visit the clean room facility there to actually see the Hipparcos satellite being assembled.
Wow, to see the machine that would use their painstakingly created list.
Yeah, seeing that complex piece of engineering, knowing it was built upon this foundation they'd spent years constructing, must have been quite something.
And it just throws the contrast with Gaia into such sharp relief, doesn't it?
It really does.
Yeah.
As the source material points out, the concept for Gaia observe everything down to a certain faintness. A billion stars might seem simpler in some ways than picking just 120,000. But actually doing that presented its own colossal technical hurdles.
Building on everything learned from Hipparcos.
Absolutely. It's that shift, isn't it? From a highly targeted approach, driven by the limitations and the need to pre-select importance,
Hmm.
to this comprehensive survey model, where the potential for discovery lies just as much in the unexpected things you find when you look everywhere.
So, wrapping this up, what's the single biggest thing that stands out for you from this whole story of the Hipparcos Input Catalog?
For me, I think it's the sheer human element. The incredible dedication, the collaboration needed across countries and disciplines, the grappling with limitations. It wasn't just about data. It was about people wrestling with huge scientific and technical challenges. It really underscores the perseverance needed for these foundational steps in science.
Yeah, I agree. And for everyone listening, I think understanding this backstory gives such valuable context. We see these amazing data sets from Gaia now, but knowing the kind of monumental effort that went into its predecessor, it really makes you appreciate how science builds, step by painstaking step. It wasn't easy.
Definitely not. It makes you appreciate the hard-won nature of that knowledge.
So maybe a final thought to leave people with.
Yeah, how about this? Considering the intense debate and, frankly, the agony that went into selecting maybe 120,000 important stars for Hipparcos, what completely unexpected discoveries might now be lurking in the Gaia data simply because it didn't prejudge, because it observed everything?
Or maybe, thinking about how they defined important back then, how might our own priorities for what's important to observe change in the next few decades now that we have these massive unbiased surveys? What questions will we think are the most vital?
Interesting questions. Food for thought.